Меня зовут Анастасия Черникова.
Anastasia Chernikova. We work in Syntacore. We do processor cores made in Russia, and I am in charge of compilators of developing, and we're going to talk about open source from its fundamentals and about the programs that you all know. So let me start, and I will give the floor to Anastasia later. So let me try to not to be in the way of the presentation. Who has heard about open architecture RISC-V? Alpha I have not heard, and that's why I have two slides about this, because where open source starts, it starts when we make a system of commons, when we make architecture, and RISC-V is free and is open system of commons. So it means that at previous presentation there was a question. So if we do a system of commons ARM, do you know what is system of commons? So you are making this processor, and ARM then calls your license, as it happened to one large Russian manufacturer. And if instruction set is controlled by a vendor, it's like software which is controlled by a vendor. It's like Linux in the world of microprocessors, like OpenGL in the world of microprocessors, because RISC-V is controlled by the committee, which was established in 2015, this committee, and it numbers more than 4,000 companies that determine this set of instructions. In Russian, there is Russian RISC-V Alliance, and it's not only open but also expandable instruction set. It means that you are choosing the basic instruction set according to your taste. After choosing basic instruction set, you can make any expansions, such as in a basic instruction set, you don't have multiplication, and it could be a small multi-controller. So you're making an M extension, and you add it, and every time when you make a hardware, you know, a string, and there are hundreds and dozens of standardized extensions. So if you want to support quick photography and communicate this to people who are writing software, you are supporting ZKN, and all standard extensions are Z and then some letters. And if you would like to support some extension which is not standardized by the committee, such as Ghost Russian cryptography, which is called XK-Ghost, you add this, and in your processor you support instructions which software can use for cryptography. And each solution, each standardized extension is open. So you can read it, and everyone can use it, and it's quite convenient. If you want to have quick cryptography, you can include a vector crypt. Syntacore makes a line of cores, so you may see here a list, and at the top of each square there is a list of extensions from SCR1. So if you can disassemble your gas meter, which supports only R232M, up to SCR9, which supports a lot of extensions, compress instructions, atomics, and even vector extensions. So it's interesting that our open source starts from open command system, open instruction sets, and can the processor core be open source? It's a very interesting question, and I'll give the floor to Anastasia to cover this. Thank you, Konstantin. Before we go deep into the architecture, is it possible to have open processor cores? Initially, it sounds like science fiction, because processors are made by big corporations and they use commercial secret patents, but open code became a standard in software. Why don't we apply this to hardware? If we have access to open architecture, which provides a lot of flexibility to us, we can design, we can change and adopt cores to our goals, which makes their manufacturing more efficient. Let's start with design. And on the right, you have how SCR1 looks like. Those that understand, wait, not so many. So let's talk about one-tact processors. They're very simple. They perform all instruction in one tact. And such processors are not made any longer, they are not efficient due to how they're built and how they work with instructions. However, it describes how they work in those training problems. There are also multi-tact processors, how the instruction is loaded, executed, working with registers. And the advantage of multi-actor processors is that instructions are split into several acts, and they can work with a lot of memory. With one memory for instructions. There is also a conveyor processor when instructions are performed or executed at the same time. When one is loaded, the second is decoded, and third is at the execution stage. Then we split them in such a way in order to perform our instructions most efficiently. There is a conveyor process, instructions are split, and that's how we get the best performance. Such type processors are used everywhere, and you can take any device where the processors are of conveyor type. Example from David and Sarah Harris' book. The link is at the bottom, and you can see how at the conveyor processor there is a distribution for different processes for the pipeline, and this may work incorrectly. So the problem is, what is wrong here? So you can find the answer in that book. Now let's look at the conveyor stages. First stage is instruction fetch, and when it's reading from the memory, updating the program counter, and then there is a decoding stage when we decode opcodes, reading registers, and checking dependencies of our instructions. And then we are executing. We work with ALU, arithmetics, calculating addresses and conversion conditions. Then there is a memory block, access, reading and writing into memory, the longest block, and the last is writing into register, results processing, and instruction execution. SCR1 is example of this processor, and this code is open code. You can download this and you can look how it works. SCR1 is based on 32-bit RISC-V architecture, and it's ISO RV32I and RV32E. It also can be compressed, and it's used into microcontrollers and IoT, and in many training educational projects. SCR1 could have up to 4 stages of conveyors. The advantage is that the number of conveyors could be configured depending on specific tasks. Interesting part is interface. It's HB and AXI interface, and also FLIC interface. We discussed interfaces. It's important when designing any core and of what to make from the beginning. Interface is a system when processor components can interact. So the interaction could be inside the core, between ALU block and register file, and also using interface there is interaction from outside of the core with memory or other periphery. A large advantage of the interface that it is a module. So having written this interface once, we can reuse these blocks, and this approach is clear for many developers from inside. So to develop interfaces, we need some methodology. How can we find information, how to write this correctly? And now let's talk about AXI and HB interfaces, which are most popular. And inside the core, there could be different interfaces, how we can configure them before launching. And in this case, I will talk about SCR1 core, which has both interfaces. So we can assemble them with one or the other interface depending on the tasks. Both interfaces have been developed in ARM, and AXI is an interface which is faster, more with higher performance, but is more complex. It is simplifying many tasks, and but to verify, to understand that it works correctly is more difficult. HB is more simple, is older, has a simple design and simpler verification. An example of using cores SCR1 is Amur microcontroller. It uses SCR1 core RV32IC architecture. It's used for training projects. And we are talking about the same core SCR1, but there were much more of them. One of the alternatives is IBEX core, which is developed by a low-risk company and is also available as open source on the market. This conveyor has 2 stages only. The architecture RV32 and its style link interface, or HB. the main priority of creating this core was to work with devices which have battery charged and powered. So they are often using IBEX battery-based devices. It's quite a simple core. Here we have a more interesting variant, 6 conveyor stages, and principles are much more complex. 64-bit architecture, which is RV64GC as a priority, using AXI interface, which is much faster than HB from the previous option, and supporting Unix like systems. And we have developed a cache subsystem. So the there is yet room to improve. Black Parrot is a vendor. They've developed a core based on RV64GC. The advantage is that these are vendors that can work as a group. And here we have not one core, but several cores. You can see how many cores are in your laptop, and that is a big advantage. This Black Parrot can work as 4 cores together, and they are now improving to use more cores in one processor. So we discussed different cores, how they are designed from inside. But before making a model in hardware, we need to understand that everything works fine. It's designed correctly. For that, we need some test environment and test bench. It is also written around our code, around core architecture, and is made of different components. There is a memory model, some monitors, which monitors the system, how different parameters are changing. And when we design some test benches, it's important to know that it would be clear to our colleagues that are writing the code together with us, and that it could be extensible code when we can test some part to the end, so that we could add some code and not to rewrite the whole code. For that, we need some methodology like UVM. UVM is a standard methodology to verify Verilog language systems. So we have DUTE, device under test. We have sequencer, which takes from somewhere the thread of tests, sending it to the driver, and this driver thread is sent to the device under test and sends this to the monitor, which monitors input and output data, and scoreboard, which compares the data as a etalon and the result of working with DUTE, how it works from inside. So we need to test our equipment, see how it works, but where do we take the tests from? There should be a lot of tests, there should be of quality, and Konstantin will discuss about this. Thank you, Nastya. There should be some intrigue from what Nastya said. It's so difficult, even if it's open source. If you need a full verification for this schematics, imagine complex interfaces. If there is a small bug in AXI interface, how long are you going to catch it. And you need to take a lot of tests. The first idea for tests is, of course, to take existing programs, like loading Linux core. If you don't have microcontrollers of Linux that are working on your core, you can load Linux core to test. So if you need to take something existing, you need to compile something existing first. And that leads us to the main thing which we do together with Nastya is open compilers. Compile infrastructure, LV. So let's try to compile and then generate tests without leaving open source. We are working on Syntaccord toolkit, which is an open toolkit, which is freely distributed, and there will be a QR code at the end to download it, so you'll be able to download it at the end. Just remember that it's available. It includes lots of tools, including two toolchain, LVM-based toolchain and GCC-based toolchain. LVM-based tool chamber, it's a license because GCC is too much open source. In GCC, you cannot do anything without showing this to the whole world, and sometimes you don't want to show everything to the whole world. And the second advantage of LLVM is module-based. GCC is less module-based. It does not allow to build convenient tools, but it has some advantages. With GCC, there is quite developed alternative. So that's why there is a connection of one toolchain to another toolchain by complex methods. And you can take Clang compiler and then assemble needed assembler to the required assemblers and use it as a necessary link. You can do this using GNU linked. This could be integrated if you have a root with GCC toolchain. There is sysroot as a special folder heading for applicable libraries. We can do that in LVM, and we can make some fine adjustment options for each core which supports our toolchain. Fine adjustment options, a compiler is very complex logic, and even machine-independent optimization unroll may impact code quality depending on the architecture. Because in one case, code size is important. You don't need to unroll much, and in some case, you have big instruction cache, and you may unroll infinitely. But I'd like to focus on a different thing, what we need now. It's a planning model. When Anastasia was talking about the phases of processor work, they are available on the slide. When you're writing a compiler, you are taking the same phases and you unroll it for the input instructions. And as for the scheduler, it is unrolled to minimize delays in the conveyor. So our technology is very much interacted. So LLVM is not only infrastructure compiler, but it's a universal source of architecture information. So we're using it now to solve testing of processors as a system verification. But why do we limit only with processor? Let's think about system verification. What we would like to verify. We're not starting from the processor. We're not launching something on the processor. First, we have a number of models, and even microprocessor could be perceived as a model. So let's look at the test generation for different levels of models. Functional models such as CAM, transactional model, cycle-based model, Gen5 or VCS, logical design on FPC, and how the tests look for each of these models. For example, if you have a functional model and you need to test logical design, how would you do that? Obviously, if you have a model and you would like to solve its verification, you need to check that this model satisfies specification which it generates. So verification task is to check specification. And if you have a working functional model, but you are doubting its logical design, what would you do? You would generate a lot of tests and would apply them to model under test and golden model, whatever it is. But where would you take these instructions from? These instructions you would take from instruction sequence generator, which is part of the LVM ecosystem. And in that case, it's not upstreamed into LVM, but it's available on GitHub Syntaccord. It's called LVM Snippy, and let me elaborate on this, how to test it. It tests everything where you need a stream of instructions. You can test functional simulators such as SPAL, Camel, and LVM. You can also test debug information to annotate it. So how this generator looks in the most simple case, using this GitHub link, you may download it, have a look whether it will be useful for your tasks, because we would like to build a big open source community around it. We have a generator which takes histogram with instructions. We are adding them, norming them to 1, and then we're getting this generation, we're getting the instruction sequence. But in the world there are millions of such generators. Why do we need to write another one? The thing is that LVM Snippy is a part of LVM, and a lot of things where many other generators that are available on the internet, it's taken from LVM Open System. It takes the instruction description and machine YARM, and inside that generator you can concentrate on generation logic, the management flow. So how this looks like. SNP is used for training processes, and Nastya has mentioned UVM methodology, which is still under development.
So if you write a runner that will integrate several snippets, run them, and include something like a trace, there are examples of positive use of this generator in open source. And we have an open LVM infrastructure. We've already seen that we can compile using it. We've seen that we can generate tests using it. And what else can we do with its help? You get an impression that we can do a lot of things, but let me pass the mic to Nastya so that she would tell you about the surprising things that we can do. Thank you, Konstantin. So, on the whole, the LLVM system offers a huge set of different tools that allow you deal with very diverse situations. But today, we're going to talk about one more of those. So, it's a tool for benchmarking. Actually, the benchmarking tool is quite important thing because it allows you to find bottlenecks in the system. Also, it helps sort out within the LVM ecosystem. The benchmarking task consists of different aspects. For instance, to verify how correctly the device works with memory, whether the information gets to the right caches, how interaction happens between different systems. And with this part, unfortunately, the tool that had been available is not going to help us. But if we have some instruction set and we need to know how long it will take for the instruction to run, or the throughput of this instruction, it's exactly in this case that LLVM exegesis can help us. So it's basically an LLVM tool that is distributed together with the compiler, and this tool generates an ELF file that either the tool itself or the file can automatically be run. So to understand the number of cycles needed for the instruction to be processed, or some other information. Now let's talk about how it works in a nutshell. So at the input, an instruction or an instruction set arrives at LLVM exegesis, and then the tool generates a cycle that repeats the pattern that we're interested in many times over, for instance, 100,000 times. And then at the output, we get an ELF file that calls the JIT tool and run the device so that the device gets this file and gets all the characteristics that we've asked. Or there's a more difficult way, a complex way that allows us running on other devices. For instance, we run it on our laptop, get a file or a binary file at the output, and together with test bench and wrapper, we're getting a complete program that we can run on another device and measure how many cycles are required to process a certain instruction, or the throughput. Just a second. So where and what for we need that? One of the ways to apply it is for different optimizations within the compiler. One of them is critical path optimization. To understand how it works, we take a program and build a weighted oriented graph. As weighted apexes, we'll take the instructions for which as weights we assign the number of cycles to perform each instruction. The critical way is shown in the slide in red. This is the path that takes the longest. It defines the time of our program's operation, and our main task is to reduce it. And another way is to use it within scheduling models within LLVM. Konstantin has already mentioned them. And the slide shows a scheduling model for the Rocket processor. And it's clearly seen that dividing a 32-bit number, in one case you need 33 cycles, in another one 34 cycles. That will determine how the optimization will work. So this tool can help us. It was initially designed as a tool to build schedule models within an LLVM in a correct way. So we've talked about a lot of low-level individual components, how the hardware works, how the CPUs work, what kinds of CPUs exist. Then we discuss compilers and what sits next to compilers, the tools that help us develop the environment. But now, let's switch to the rest of the software and what happens above the level we've discussed. And it's Konstantin that's going to talk about that. So, imagine that you have taken an open core, have taken open tools, and loaded an open source operating system, Linux, or not yet loaded. For instance, you are designing a cellular phone to use another CPU rather than ARM. Are you going to run into some problems if you use the RISC-V architecture? Again, because in a certain sense, it's down to you to use RISC-V because it's open. You don't want to get into a vendor lock. Being a conscientious person, you should be interested in using open source operating systems. It's a surprise, but the main problem about RISC-V is exactly in where its advantages are. Look, Nastya was showing different open source cores with different sets of extension, and RISC-V kind of provokes you. It kind of tells you, make your own extension, build your own extension, get into an agreement with some Chinese producer, let them build a CPU with you for this extension, or take an open source core, and contract somebody to build an extension. So you've built it and produced it, and then a friend comes to you developing Android and asks you, look, what's the set of extensions I am to build my Android to, or even worse, your friend comes to you developing glibc and asks, what's the set of extensions that I should rewrite glibc? And here you start feeling bad. It's an unexpected problem that exists in a situation where you have extensible instruction sets. It doesn't exist in the ARM world because when a development comes to them, under which should I discuss should I build glibc? It's like asking what the political party were talking about in the Soviet Union. There was just one party, and these problems occur quite often in graphics APIs. Because with which extensions should I compile the program in GL? And this problem is solved with the help of a profile in RISC-V. When I said that RISC-V had a lot of extensions, I was, it was an understatement. There are very many, huge number of extensions. So this slide shows only the mandatory extension of RV64, RV822U64. It's a common profile in the standard of 2022. So we see that the number of only mandatory extensions, it takes a table of 4 columns, and there are 4 optional extensions. For instance, ZKN is exactly the cryptography that I was talking about, and V is just vector extensions. So you can have vector extensions, and then your phone will work much faster. At least it will do memcpa much faster. And so RISC-V plus profiles make RISC-V to a certain extent a normal operating system. It's at this moment that you need to understand that you'll have to write in bitroot. So which configuration you should orient yourself at when you got the RISC-V hardware. And in a sense, the profile line gets better with time, and the software gets better with time, including the list of software that's available for RISC-V. RISC-V. And high-level software, if we roll back into 2010, at that time it was virtually in existence. In 2010, they were only designing the instruction set, and the first bare metal prototypes only appeared by the year 2017. But as early as in 2021, and I, for one, started to seriously working on RISC-V in 2021. I mean, on RISC-V compilers. So as early as 2021, first Linux-capable hardware started appearing. The first compilers for AI started appearing. Drivers started appearing in a large number. And now, in 2024, 2025, RISC-V has developed to the extent where we have mobile server solutions, where we see vector extensions actively developing, including vector cryptography. For instance, LLVM now sees a huge growth of RISC-V vectoring commits, because RISC-V has a very interesting scalable vectorization. If somebody of you is not aware of how vectorization, how RISC-V vectorization is built, I strongly recommend you to delve into that. And a lot of processes. So this is the biggest selling point about the open architecture. Just imagine that something has been added to ARM. Well, wish you luck. But if you want something added to RISC-V, more likely than not, some Chinese company has already done that. So this diversity, when open source code supports you from the very start to the final open source software, such as, for instance, when you run Chromium, that puts you into the world of open source software development. And the world of open source software and hardware development is the world where, as you work, the whole world is working with you. I strongly call on you. And actually, you can download this presentation using this QR code. You can leave your feedback on this QR code. It's also important for us. With this, we're done, and Nastya and I are happy to take your questions. Thank you all for your attention.
Да, можете называть номера слайдов, можете просто задавать.
Yeah, you can call the number of slides. Thank you very much for your presentation. It was exciting to listen. I got a few questions. You were talking about test instruction generators. I understand that these are just generators. It's supposed that they're going to be part of some test suite, right? Because a generator usually generates dust, and for a fully fledged test, you need to have a test framework that will verify if it is done correctly. I fully agree with you. We are talking about the instruction sequence generator, and it's exactly why I was showing that for it. Unfortunately, the clicker works rather slow here. Yeah, but here. But it needs to have some additions, and everything that is marked by blue is something you'll have to write it. Because I believe in narrowly specialized software, generating a good instruction sequence, especially if it is supposed to have branches and memory, and you'll be able to configure which addresses it will fire to and which it won't, especially if the instructions are to be responding to that, and snippet can done. So it's a very difficult task. So therefore, we've built it in such a way that it should fit with any wrapper. For instance, I left a question. The generator not only generates an ELF, but it also throws out a script. So that if you have some memory scheme, it should still be linkable. We try to do our best to make it integratable, and yes, all the users included in their own test benches, because it's what people doing verification do. Yes, clear. And perhaps these instructions have some cycles, have some loops, Well, I suggest that you listen to my other presentation. But we have a cycle counter, loop counter, and we book this register so that outside the cycle it shouldn't be used anymore. And in certain cases, we allow reading from this register. And in some cases, we allow it to be reused if you've set the place in the stack for the generator. Because with compilable structure, the compiler can do these things almost for free. Thank you. Do you use this instruction generator to verify your own process and simulator? That's exactly why we wrote it. So it's not only to verify the tool chain, so verify the processor. How do you measure the completeness of testing, the coverage, and what's the test framework? Verifiers do that. I wouldn't even tell you had I known molecular the secret, but luckily I don't even go into those details. Okay, thank you. But I still have one more question. You remember that old story when in the 1990s Intel released a set of Pentium CPUs and it had a bug in the CPU related to the divide instruction, and Intel had to partly recall this whole batch of Pentium CPUs. And after that, Intel started implementing formal verification when designing CPUs. A question, do you use formal verification in the design of the CPU? I love the formal verification, but it's a very big question. It's a very complicated question. Let me be brief. In using formal verification, there's exactly one subtle point that I've been highlighting in this room 2 presentations earlier. When the presenter was talking about SNT solvers, you run this thing that proves you that something is never going to happen, and then you don't know. So you're waiting, for instance, 30 hours, whether to press Control-C or wait another hour. So is it ever going to stop? But so we use formal verification in a limited way. For instance, formal verification to a certain extent in certain specific areas of symbolic execution using the CLI system. They can be used to select the data. And then you can load it into the generator, so the generator should supply it with database data for this instruction. We even have a commit on review in the snippet like that connects to the database. And by the way, it was built by students from St. Petersburg University. It's a very exciting area, and but it's very complicated. A formal verification of a small node is okay, but formal verification of something large is unexpectedly difficult. It's super hard. When you were talking about Control-C, perhaps you meant model checking. The biggest problem of model checking is that you have an explosion of states when you have to model too many states, and the model can take an infinite amount of time. But there are alternative ways when you have a model and run against it and compare the model of your CPU and the Fordel model. You're using reductive verification. Do you use approaches like that? You know what? I have not taken part if they use, but that's a subject that's a lot of interest to me. I dig it all the time. So there's direct task. We generate more tests and see what happens. And there's a reverse problem. We start with a situation and try to prove that it will never happen. There's a sneak generator solves the direct problem, and I would sometimes like to write something that will solve the reverse problem, but I don't have a solution so far. It's just you're saying that formal verification is very difficult, but at the same time, we all know that the system can show the presence of bugs, but does not prove their absence. I agree with that. There are a lot of statements there, and it may take a lot of time to wait. Thank you very much.
Там есть вот сотовой микрофон, может, по очереди?
Maybe we take a question from that mic. Hello. In the beginning of your presentation, you mentioned an interesting idea that RISC-V is just like Linux in operating system. And I would like to highlight a certain risk that an unpleasant incident happened in this foundation when this cancel culture touched upon Russian developers. They threw them out, stopped taking commits, taking contributions. So how about this in your case? What risk do you see? And what happens if the risk realizes and you're cut away from the chain? Well, why? What if? It has happened, and what? Nothing changed. Nobody is going to ban the development of user specifications. So we have limited ability to impact the international specification, but we can keep developing the specifications for the Russian lines. So just imagine everybody was banned from Linux, and then everybody switched to Astra Linux. So you can still develop the specification in Astra Linux. More importantly, you can continue using everything that has been developed worldwide. So you got into a fork situation. No, we haven't. We do our extensions, but a lot of other vendors that haven't been banned anywhere also built their own extensions. Everyone has a right to build extensions. It's just you can't contribute to the committee. And how do you synchronize the stories that LVM got features for others, but will not include your own? Well, we have the Syntacore development toolkit that I've shown in the slide, and which is the main things that we're working on with Nastya. It's so it's not going to appear in the main corpus, but it's going to appear here. If you have Syntacore cores, you can include this. Hello. Thank you very much for your presentation. I was lucky enough to work with one of your cores with CR1 as part of my research. And perhaps my question will seem a bit naive to you. How realistic it is at the level of the design of the software core to design the security of this core or to implement some the security checks at the level of verifying this core. Nastya, would you like to answer? Yes, please. Can I have the clicker? One of the cores we were talking about. The previous one. So on the whole, there are open source open cores that focus on security. Of those listed, perhaps this one is the most secure one, but one can take a closer look. There are cases in the open community, and it's right in the documentation where it said that focus is made on security of these things. So it really exists, and it keeps developing. Thank you. I think we have time for 2 more questions, and then we'll switch to the next presentation. Thank you very much for your presentation. I have a question about your answer to one of the previous questions. You use the phrase that you use click as a tool for symbol analysis, and you use it together with a form of verification. So how do you determine that CLI, that it makes sense to run CLI on some specific piece of code, on some specific set of instructions, to understand that it makes sense to run CLI on this set of instructions? That's easy. We run it against the entire F extension, and we don't use CLI. We use CLIF. St. Petersburg development on top. Students will soon be defending a diploma work right this summer. It's very easy. We take instructions one by one, and then we take IBM and use this model to search what kind of instructions. All of them.
Анекдот рассказать на эту тему.
And I can give you a joke about that.
Полный набор
A student took the full set of instructions for FE, the ECU parameter, 1 second for fmol, 1 second, fuse, multiply, add, a day and a half. We almost pressed Control C. So yes, that's exactly what I meant. Thank you. Good evening. Thank you for your presentation. I have two questions. Number one, do you approach the protection of power attacks,
Соответственно, это вопросы к
power supply attacks?
понимаю.
These are questions to physical design, as I understand, because side injections on the power is not even about logical design. It's just like how the heat is distributed between lanes. Yeah, but it can impact the pipeline as well. The pipeline.
Я еще раз, скорее всего, вы будете наблюдать
Once again,
воздействие.
perhaps you'll be observing this impact at the level of physical design. I never went there. I start with logical design. I understand it more than not, but all these things, when heat is generated, so the fan is rotating, and some conclusions are made. I don't know that, but what I know is that there are people in the company who perfectly understand this. They're not here, and why they're not here? There's nothing open source there. So open source ends in logical design, and then you get into the realm of, hard secrets. Okay, thank you. Question two. You had it in your presentation when you had a collapse with Micron, with Amor 32 was created. Are you planning to collab with themselves or Melandra or some other Russian producers once again, but to deep a bit better into IOTA, as it's important to see in IOTA is responsible for security. So there, it must make sense to foresee some security mechanisms related to the update of firmware at the hardware level. Why hasn't everybody laughed in the room? It's a great joke that the letter S in IoT is responsible for security. It's not present there. Look, regarding collabs, as I said, SCR1 is an open source core. The vendor can just download it. They don't even need to buy it from us. They can download it from GitHub and then do whatever they want. Yes, so they build a cool Amor microcontroller. And by the way, Nasya didn't say, it was printed in Russia at the Micron fab. So can anything else be done for IoT focus on security? Yes, of course they can. You can. Well, the question is not that abstract, whether they can or not. The capabilities, of course, are there. But I'm interested in specifics. Are there any plans? Well, had I ever known about such plans, I wouldn't have the right of publicly disclose them. That would be something like a commercial secret. Again, thankfully, I'm head of compiler development, and I'm not aware of the hardware product development. Maybe you should find some of our marketing people at the booth. Unfortunately, we don't have a Center Core booth at this conference, but maybe at some other conference. Thank you all for your questions. Nastya, Kostya, it's time for you to choose the one who gets the book from Peter Publishing House. Which question did you like the most?
Давайте сделаем ребятам чуть проще.
Let's do it this way.
Вопросы поднимите,
The
пожалуйста.
guys who are asking these questions, please raise your hands. Nastya, which question did you like the best? Did you like best?
Думаю, что вопрос про СНИПе.
I think it's the question about the snippet. Let's stop there. Okay, yeah.
Помощники в чат вам.
So you're welcome. Our assistants will hand you the great book from Peter.
Давайте поаплодируем ребятам.
So let's give a round of hand to the guys. In first place, thank you very much for your awesome presentation. That was incredible. And with this, the first day of our conference runs to an end, comes to a close. Thank you all very much. We'll be expecting to see you tomorrow online and on the site. Thank you, all of you.